This is the second video explaining in detail the approach of creating artificial digital life. You may want to check the previous video and the trailer of the series first, explaining the goal and setup of the model used. A general guideline for my approach is to keep it clean and simple. Complex structures should emerge by themselves, not because complexity was built into it right from the start. In this video we will see genomes evolving. Remember, cells were represented as point-like structures in a pixel world. Let's add a sense of orientation, that is, cells are looking up or down, to the right or to the left. The cell depicted here is looking up. If a cell is acquiring a gene for movement, it will, when activated, move one position into the direction of its orientation. The cell may also acquire genes for changing its orientation, turning it clockwise or counterclockwise by 90 degrees. In this case, the second gene will turn the orientation by 90 degrees counterclockwise. A genome can consist of many genes. Every time the cell is activated, the next gene will be executed. A round-robin fashion is used. So after the last gene was executed, we continue again with the first one. In our example, the execution of the first go gene moves the cell up for one position. If that position was already occupied by some other cell, this gene would simply be ignored. But in our case, the position is free and the cell can move. Moving will consume some extra energy. At the time of the next activation, mind that in the meantime many other cells were activated. The cell executes the second, that is the L gene, turning its orientation to the left. And again, as the genes are executed in a round-robin fashion, at the time of the next activation the cell would move one step to the left, if that position is void, then turning down. So this genome would make the cell run in a narrow circle. At least this would be the genome's intention. In reality, the actual movement may look very different, as often the cell might not execute a movement due to the next position not being void. Mind that a change in orientation is always possible, so these turn left and turn right genes are always executed. Now, how a genome is created and shaped. In the beginning, cells don't have a genome at all. And when they create an offspring, they will inherit their empty genome. But with a certain probability, I'm usually applying 1 out of 1,000, a gene can appear. Once a cell has acquired a genome, in this way, it will again inherit this genome to its offsprings. Again, in most cases, every gene is copied perfectly, but in one case out of 1,000, a mutation will occur. The gene will either be modified to a random value, or it will be deleted, or a new gene will appear in addition. As you can see in the picture, in most cases, a mutation will lead to a simple change. Also note that the deletion of a gene is more likely than an addition. This has a very important consequence. In order for genomes to grow, there need to be an evolutionary pressure. That is, the bigger genome has to provide an advantage to survival. Without such an advantage, mutation rates will tend to shorten genomes. Now, let's see all this in action. And for the sake of simplicity, let's omit turn left and turn right genes and allow only go genes. Within 50 cycles, the first mutation appeared, creating a genome with a go gene. Now we see another group of moving cells, this time going up, after less than 300 cycles. We are using colors to mark the varying genomes. The green cells have no genome at all. The gray cells have a single go gene. Note how the gray cells are outnumbering the green cells. Because of their ability to move, they run across a lot of food, thus gaining energy and being able to reproduce quickly. After 2,500 cycles, almost all initial green cells are gone. Cells without a genome for movement simply can't compete. Nevertheless, mind that you will spot a green cell from time to time, being an offspring that lost its genome due to mutation. After 3,000 cycles, another new species occurred, as we can tell from the blue color. Let's fast forward. After 8,000 cycles, yet another new species is occurring. Let's have a look at the different species at the end. The dominant species is the one with one Go gene, with more than 13,000 cells. But interesting enough, there are also little populations of Go-Go genomes and even of Go-Go-Go genomes. How can that be, given the facts that an additional Go gene does not provide any advantage to survival, and the applied mutation rates tend to shorten genomes? It's because of the probabilistic nature of evolution and an important first lesson. We will come back to this. Now let's go for the next step and allow evolution to make use of all three genes for movement. That is, go ahead one step, turn left, and turn right. Again, in the beginning, we are starting with a few cells not possessing any genome yet. Food is rather scarce. It takes some time before they spread. After 2,000 cycles, the first genome for movement has appeared. As a reminder, a cycle is the time by which all existing cells have been activated once. This is a statistical measure though. If there are 10,000 cells, we will do 10,000 activations, but cells are picked randomly. So some cells might not be activated at all, while others are activated more than once. But anyway, this method is fair to cells in the long run because of the law of large numbers. Like in the last simulation, we see a blue species evolve with one Go gene and a brown one with two Go genes. The initial green cells without a genome are slowly dying out. And now we will witness a very interesting phenomenon in evolution. The current situation will last for a long time without visible progress. We have to fast forward for more than 100,000 cycles, and you probably wouldn't expect any change whatsoever. But see what's happening. A new species is appearing, colored in light green, with a very different way of moving. It's disappearing again, and a species in ochre appears. Now that evolution has successfully made use of genes for turning the orientation of cells, these species are not only spreading, but are also the basis for more species. We see this even more clearly when fast forwarding again. The changes now are more gradual, but apparently genomes are evolving. And in fact, this is what we see when analyzing the situation. After 160,000 cycles, there is a clear winner. More than 97% of all cells are of the greenish type, with a genome reading Go, turn left, Go, 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 turn right. From now on, we will represent these genes by numbers, 0 standing for Go, -1 for left, and 1 for right. But it is also true that other types have survived as well. This is the list of all surviving genomes. You may be surprised about this diversity, and you probably haven't spotted those cells painted in the various colors you see in this picture. But of course, the diversity of genomes was much bigger over time. Just a few survived. Most of them went extinct. This is the list of extinct genomes. The very first one in the upper left corner is the empty genome of the cells we started with. The one below is the first one that ever moved with a single Go gene. They have all gone. Of all the different color cells that ever lived, only a few made it to the end. We have to bear in mind that the situation after 160,000 cycles is not the end of time. Also, this situation is just a snapshot in the flow of evolution. Genomes were growing because it apparently helped to find more food this way. Would genomes go on growing forever? Or is there a limit beyond growth does not provide any advantage anymore? Let's have a look at the graph depicting genome growth beyond our 160,000 cycles. This is the average genome size over the whole population for 3 million cycles. We see genomes do not go on growing forever. The genome size reaches a size of 80 genes after 430,000 cycles and stays in a band between 8 and 10 genes going forward. One more question comes to mind. We have seen quite a variety of genome types, but we could ask, which genome types were dominating the population, say, when checking after each period of 10,000 cycles? The result is surprisingly uniform. Once the basis is established, we clearly see a pattern. In a way, it's all the same genome family. With this kind of analysis, we can address more interesting scenarios. For example, whether differing regions will be dominated by differing genomes. And we can also address one of the big outstanding questions regarding evolution. That is, whether all intermediates have to be advantageous. That discussion between biologists has been going on for a long time. At least within our simple model, we can provide a clear answer to this. The question and answer will be discussed in detail in the next video. So stay tuned and don't forget to subscribe.